So hello, I'm Nitin Dahad, Editor-in-Chief of Embedded.com, and I'm here for the Fireside Chat with some of our key speakers, with Dave Patterson, Krista Asunovich, and Chris Latner. I'm going to ask them to introduce themselves, and then we'll launch into a discussion about some of the topics around RISC-V that I'm sure you're all wanting to listen to. So let me start with you, Dave. Tell me just a quick intro. I mean, no, you don't really need an intro, but for the audience, please tell us.
I'm Dave Patterson. I've been a professor at Berkeley for more than 40 years. In fact, Krista was one of my first students when I taught computer architecture at Berkeley. I've retired from Berkeley as emeritus, and I started working at Google 4 years ago.
Excellent. Okay. Krista, and again, yeah, anybody in the RISC-V community knows who you are, but just give us a little bit of an introduction.
Okay, yeah. Krista Asunovich, so I'm a professor at Berkeley, ECS department. I was a long ago student at Dave's. I'm also a co-founder at Sci-Fi and chief architect there, as well as chairman of the board of the RISC-V Foundation.
Thank you. And Chris Latner, please tell us a quick intro of yourself.
Sure. My name is Chris Latner. I've driven a long range of compiler language and other system software technology, things like LLVM, Clang, Swift programming language. These days, I'm running the engineering and product team at Sci-Fi.
Excellent. Okay. So we just had the talk from Krista on the next 10 years for RISC-V. Now, maybe let's just go backwards a little bit, and can we sort of just get an idea from all of you, maybe starting with Krista or Dave, what is this the vision that you had when you created the architecture? Is that achieved what you think, or where is it still sort of got to go? Should we start with Krista?
Sure. So I think one thing to realize when we started this, we had no clue it would get this big, this fast. And so in terms of meeting our expectations, it's way, way, way beyond anything we ever imagined. So it's way bigger. This moves way faster than we ever thought. And people are using it in all these different places we never imagined. So it's just really way beyond any expectations we had at the time.
I would say about 6 years ago, we got interest from companies, and then we saw that there was this thirst for an open architecture and why there was a thirst. And I think once we understood that, then we raised our expectations. And I think Krista's slides started using the world domination in his slides. So we didn't see any technical reason why it couldn't become the most popular instruction set. And so we wanted to see how far it would go.
Okay. And Chris, tell me what you think where we are right now with RISC-V.
I think RISC-V is super exciting. It's made a lot of progress, but I still also think there's a long ways for it to go still. And so I think that even though it's exceeding the expectations of the founders, I still think that we as a community can drive it further, much farther and faster, and there's a lot of room ahead of us.
Okay. And when you say a lot of room ahead of us, maybe we'll go into a little bit of that in terms of what's missing. But where do you think we are right now with in terms of? I'm going to sort of ask in terms of mainstream. Are we? Is it there yet? Is it there in terms of replacing other architectures? Or I know you feel it is quite well forward, but then maybe there's a little bit more that needs to be done to say for it to be sort of replacing an x86 or an ARM, for example. Who would like to?
I think that I can just start by saying I think that RISC-V is far better suited for many applications today than x86 is, for example, and scales up and down. And I think that's a pretty unique aspect of the instruction set. I think that RISC-V is also much broader than just the instruction set, and this is something you can see in the RISC-V Foundation and standardizing in a whole slice of the ecosystem, which I think is extremely powerful, and it's something that, again, isn't just about the instruction set. So I think that what I've seen is it's already becoming mainstream, And there's a groundswell of designs and wins that are happening right now. And some of these things take time to get to the market, but I think it's very much there.
Okay. Good. Krista, I think you have something to say, obviously, on that question.
Yeah, I think one thing is like just building on what Chris just said, in the open source software community, people are used to things happening very quickly, and they're obviously very philosophically aligned with RISC-V. But in the chip industry, it takes a while from when something is designed in to the chip is taped out till the product is, actually qualified and ready for production. So that's a kind of 2-3 year process. So I think you're just starting now to see things that were started a couple of years ago and now just emerging, and there is a large number of these things. We also see major companies already announce products that use RISC-V. The NVIDIA, all their GPUs ship a RISC-V. Samsung, their handsets include RISC-V. Qualcomm, they've said those handsets. So these are mass market volume production parts right now that use RISC-V. So in that sense, it's already mainstream. And I think over the next year or two, you see even more products, like high volume products that are using RISC-V. So I think it's already mainstream in quite a few areas.
But before we go to Dave, why do you think there's the narrative then that RISC-V is yet to go mainstream? Where does that come from? Why are we hearing that, at least in the media?
Well, I'll answer. RISC-V is a revolutionary concept for hardware. Instruction sets up until RISC-V have been proprietary and are tied to the fortunes of that company. So my friend John Hennessy started MIPS 35 years ago, and it's now the 7th company. So, but how do you compete against an open concept? How do you market against that? Well, it's very difficult because people love the idea of being open. So there are competing organizations that are seeding doubts especially with reporters about why isn't it as popular as it is? Because it's kind of hard to go out and take on something like this head on and say it's a bad idea or it's not going to work. But you can this is the old IBM thing of fear and certainly in doubt. You can do FUD attacks in RISC-V. But I think because it takes a couple of years between the company makes a decision and a product comes out. And even then, you can remember that Intel had to do an advertising campaign that was Intel inside, because when you buy a car, you don't see RISC-V on the chrome on the side of the car, right? If they have RISC-V, so it's hard to know it's being used. So it takes a couple of years, and you don't really advertise it. It's hard to figure out for hardware. So it's really popular, and it's going to be very clear next year or so just how popular it is.
And what will it take then for people to change that narrative then and say, well, it is there? Is it a question of the RISC-V organization saying, it is in all of these and giving some real examples of where it is? I know Krista just mentioned some names. We don't normally just hear those names associated with RISC-V. What will it take?
I think one thing to realize, we at the foundation, RISC-V International, we do have this issue that a lot of the people who are using it are not quite ready to be public about all their use cases yet. This is for their own business reasons. They have delicate negotiations to do and things along the side. So they're often hesitant to come out openly, say they use RISC-V in big ways. But that has been diminishing over time as it became clear this is just, yes, it's a standard thing people are doing. And I think that's part of how it will become more known mainstream. I think also when the consumer level, people don't care about instruction sets unless something breaks. So I don't care what the instruction set is in my toothbrush. I don't care what it is in my microwave. It's whatever it is. And so most consumers don't really care about instruction set. It only shows up in devices that run third-party software and say, oh, I bought this tablet that runs Windows on ARM, for example, but actually the apps don't work. Then the user's like, oh, something's broken. And so in terms of real mainstream, that's when so when people are buying, a laptop that's based on RISC-V silicon or a smartphone based on RISC-V silicon, and they see they have to use the RISC-V App Store to get the apps, then they'll kind of be aware of RISC-V. But to be truly mainstream, that's when you unfortunately, you become well known to the consumer only when things break, it seems, in terms of instruction sets. So,
okay. And is the business model...
That reminds me of the story. So why did everybody get to know the word Pentium? because of the Pentium floating point bug. So when Intel screwed up and everybody talked about Pentium, it actually got the brand name around. So maybe that's what we need to do. We need to have a disaster with RISC-V, so it's in the newspaper, and then we'll have name recognition for RISC-V.
I don't think we have an issue with the name recognition. I think it's a question of market traction, but it's quite interesting. Sorry, not in terms of market traction, in terms of perceived market traction. So it's quite interesting. But does business model have anything to do with it? I mean, because it's open source, you know, people think, oh, I won't be able to make money because it's free or whatever. Or is there something wrong there, do you think?
Yeah, I think NVIDIA is making quite a bit of money using RISC-V. So I think that's just, I think also there's a problem here that people equate RISC-V with open source, and that's wrong. So like I keep trying to explain to people, RISC-V is not an open source processor. RISC-V is an open specification. It's a standard. We have lots of standards in the industry. This should not be that. It's surprising how hard it is to get across this concept, given how many open standards we build on, like Ethernet. Yes. People say, oh, Ethernet's an open standard, and open to Cisco. How can they ever make any money? Or, you know, it's just an open standard. There's lots of opportunities to make money. It doesn't only, but the great thing about being open is that you enable open source. And what's great is we can have open source CPUs now. And that's really driving this boom in open source hardware. But you should separate that from RISC-V as an open standard, as another industry standard.
Okay. All right. An open standard, open architecture, what are the implications for security? And I think, you know, with a connected world, with all of these sort of low power connected products, security is going to be an issue. And I think, Dave, you know, you made quite a good point. You know, maybe there needs to be a disaster for something to happen, but is security the thing, or is it pretty good on security already?
Well, I think what's kind of big picture is it's embarrassing, having been in the field the longest of the people here. It's embarrassing how bad security is, but we're enabling, you know, purple-haired hackers all over the world to attack our families and hold them for ransom until they pay up. And are we ever going to make progress in security? So I think pretty clearly we're not going to have a software-only solution because that hasn't worked yet. We're going to need to modify the hardware. And the problem with proprietary instruction sets, assuming we have to change the instruction set, that's a really slow process. So I think for a few years we've been saying RISC-V is this tremendous opportunity. It's an open architecture, there's open source software stack, and open hardware implementations, plus field programmable gate arrays that can run those open implementations, so the security community can innovate and try it out on the internet. So what's already happened is DARPA embraced that, and there's a program, SCIF, and I think it's FET is the name of it, where they funded 4 different architecture attempts, did a head-to-head competition, put it on the internet, and offered bounty if they found bugs. And so we did an architecture experiment which compared capability-based architectures, which is an old idea that's been done by the Cherry thing at Cambridge, a security monitor from Lockheed, I guess discovering it, a version of Enclave using the Keystone project from MIT, and then really an idea I really like is the Morpheus project by Todd Huston at Michigan. And that one, he just encrypts pointers and dynamically changes them all the time. And all of this experiment, which was run by DARPA, all use RISC-V. Yeah, all using FPGAs, using AMDA, and they've already done the experiment. It was July, September. So I'm looking forward to hearing the results. But finally, some reason to have hope that, you know, security, we will not be plagued with security, insecure computers for the rest of our lives. Maybe there's some progress being made. So this could be an important milestone once we hear the answers, how this experiment turned out, in a way to make progress very rapidly that RISC-V is going to enable.
And I was at a conversation with somebody in the RISC-V summit in Zurich last year, and they were telling me how the architecture, RISC-V architecture, is inherently got some sort of bits in there which enable strong security. Krista or Chris, do you want to sort of elaborate on that a little bit?
I can go ahead. So when we designed the architecture, we thought about security quite a bit early on, and the extra piece we added is that there's a sort of machine mode that lives underneath supervisor mode, underneath user mode. And that machine mode is where you can run a security monitor. So you don't have to trust all of your rich operating systems, something like Linux, in order to isolate the machine. So you can view it as a very lightweight layer that's underneath the OS. We built in from the very beginning. Also, we worked hard on avoiding virtualization holes and other stuff that would get in the way of adding security features later. So it was always a concern. And when we, for example, building these extra privilege modes, we'd allow them to delegate interrupts out of that mode. So you would reduce the trusted code base in the security monitor at the bottom. So there's a lot of thought put in initially, but there's a lot more to do. So there's, a wide range of other things people would like to do. I think that there is a, Cambrian explosion of security ideas for architecture, and like sifting through that, because some of these are very intrusive in the CPU, and figuring out, is this really an effective approach? That's, so RISC-V enables that experimentation, but it's going to take some while to sift through all these different competing ideas that a lot of them are very intrusive. So, hopefully we'll find a good one in there, but we're enabling that experimentation.
Okay. Can you see some kind of standard architecture like some of the other processors architectures have created around it to sort of enable people to build even stronger security?
To me, one of the big differences between RISC-V and other architectures is that typically when you have a proprietary instruction set, your single source or nearly single source vendor is investing at the high end. And so they'll continue to push their roadmap forward and invest on the latest and greatest new CPU they're working on. But security affects everything. And so even the low end, the tiny embedded cores need security. And so I think that one of the major advantages that RISC-V has is, as an ecosystem play, it enables, you take Spectre or Meltdown, like things like these that come up out of nowhere. Having those addressed at every point in the space adds value and adds a lot of user benefit for the entire ecosystem. And if you look at a classic core that was targeted a small footprint, well, that may have been sitting on the shelf for 10 years and hasn't been dusted off by the vendor, and they don't have any economic interest in investing into it. And so there can be no other way to get a solution other than RISC-V in these spaces. And as the attack surface is quite broad, and as new problems creep up in the ecosystem, I think that I see RISC-V is just moving much faster because you have this multi-source approach. You have multiple vendors all kind of competing in a friendly way to differentiate their designs.
Okay. And I mean, that segues into maybe a little bit of a different question. How far are we behind, say, for example, ARM and Intel in terms of software and tools and support? Maybe Chris, you might want to lead on that one.
Sure. Well, I think there's good news, and there's also not yet done news. So good news, we have a huge span of the open source ecosystem up and ready and going. Tool chains like LLVM and GCC all have good support for RISC-V. Linux is working, tons of applications are ported. There are big distros that run RISC-V. So I think that there's a lot of early promising signs. I think there's a couple of challenges, one of which is that when you look to the proprietary world, Windows, for example, doesn't run RISC-V today, as far as I know. Android is another frontier that is yet to be conquered. I think that when I look at RISC-V beyond the base instruction set also, vectors, for example, are still a pretty new technology. And there's a lot of work to be done with vectors. And vectors are quite interesting for the software world for a couple of reasons. One of which is they're relatively new. The standardization is just completing now with RISC-V Vector 1.0. The other side of it is that it's a very different design than most other chips have. And so it's a scalable variable length design. And most software developers out there are used to SIMD. And so they're used to working with 4x floats or something. And so a lot of the software ecosystem, I think, will need to be rethought and look at vectors and their new capabilities with a fresh light. And I think that all of the benefit of that will take some time to percolate through the ecosystem. And so parts of the domain that are already fairly compiler-centric, things like the machine learning domain where you have a lot of new compiler domains, the compiler techniques and stuff like this happening, I think are the best prepared for that. But the bare metal embedded software that people infrequently touch, I think is going to be harder to get to take advantage of vectors. And so we'll see. But RISC-V overall in the domain, I think, is already exceeding expectations. And so it's just looking at the further fringes of the technology stack as we go forward.
Who else would like to add to that, or no? Okay. So what I'd like to sort of move on to is, yeah, we talked about, you know, a lot of the architecture, the security, the software, the tools. How about in terms of, it's very broad in terms of applications, but it really does cut across everything, doesn't it? Or is there something where maybe a RISC-V is really good for? I'm hearing from you that, yeah, it's very broad and yeah, it's horizontal, but is there anything specifically that you think you want to say, maybe highlight as quite important?
Well, I would bet the ARM people would say ARM is kind of universal too, with their 32-bit and 64-bit instruction set, and I would agree. I don't think there's some technical reason that they can't be in the data centers or in microwaves, given they've got both address sizes. That applies to RISC-V too. I mean, RISC-V has already designed for a 128-bit version, right? Krista et al. Put that in, and that's kind of futuristic. But the mistake that you can make in computer architecture, the one killer mistake, is not having enough address bits. So when ARM went from 32 to 64, they changed the instruction set architecture to pull that off, when they pulled that off. So this is all, that's not going to happen for RISC-V. I don't know when we're going to need 128-bit instruction sets, 128-bit address space. We're going to need it sometime, but that's already built in. I think the other really elegant feature that, because of the academic roots of RISC-V, is whenever you teach a course, you always subset the architecture to give it the key pieces that you need to know from a student's perspective. That's pedagogically, and they can learn the rest of it later. I did that with the MIPS instruction set for Hennessy's in my textbook. That's embraced officially in RISC-V. So there's 47 instructions that all the software will run on. So this is a new characteristic of computer architecture, is only 47 instructions. I think this is one of the reasons why the security community is so excited, is they can start with a formally defined, industrial strength, valid, simple instruction set and make tremendous progress. So it's going to be the first architecture in any new kind of technology, no matter how you look at it, because it's so much easier to do than anything else out there that's serious. So I think this is an interesting, pedagogically inspired, really important characteristic that Krista and Andrew did.
I just want to talk about the adoption. So I think that Chris alluded to this too, about there are these ecosystems like Android or Windows. There's a huge existing software base that's coded native to some ISA. And those are like the most difficult to transition. It'll take a lot of work, and it may not make any economic sense to transition those. I mean, people still run IBM mainframes, software stack. People run Unisys mainframe stacks, and they figure out how to do those with translation. So those may stay as they are, but I think you have to look at all the new areas. So, where we sit at this point in history, most computing in the future will be new stuff, right? And there's all these new domains, and that's where RISC-V is an ideal match. I think nobody's designing x86 into any new domain, like just period. Like it has its place. It's not going to grow from that. It's like the 80s mainframe. This is, 80s version of the mainframe. It has its place. That's where it is. Nobody's designing that to do anything new. Other places you look at the big deal with RISC-V isn't I'd love to say it's the technology, but it's not the technology, it's the business model. It's an open ISA. And if you're building something new and you can have a lot of software, why would you trust a single vendor to manage your most important interface? I think that's the decision anybody in your domain has to make, is like, why would I not use RISC-V?
Yeah.
Why would I lock into a single vendor? Anything new, I don't see. And again, I think the audience here is maybe a lot of engineers, but if you go up the, exec into the C-suite, a lot of people are sitting there looking at this as a long-term strategic business decision. Do I want lock-in or not? and RISC-V frees me from that lock-in. And if it's a new application domain, why would I not pick the open one instead of going with a proprietary lock-in, right? So, I think, there's going to be some income software ecosystems. There's no hope of RISC-V dislodge, or there's no reason to, like there's no business reason to dislodge these things. Right. Other cases, there's a good business reason based on strategic interest. Like I don't want to be, monopolies are very good at extracting money from people. And C-suite execs know this, and they are moving away moving to RISC-V because they see the advantage there. So yeah, I think over time you'll see, it'll be more a question of why didn't you use RISC-V than should we use RISC-V?
But one of the things I keep hearing also is that when somebody has invested so much in their software, the tools, it's very difficult for them to move, because then they need to move and educate themselves as well, I guess. Are you seeing that, or I think Dave?
Well, so I think that RISC-V supports all the standard tool sets, and so there's definitely some retraining, usually at the very low level embedded side of things, but most of the tool sets are there. And so when I look at RISC-V and migration to it, I think that one of the things that we as a community should do is look to reduce the cost of friction of migration. And in addition to just generating the best possible technology, keep in mind that there are existing ecosystems out there and try to reduce that friction. I think there's a lot of opportunity for that, and embracing standards that already exist and working with other communities can help.
Yeah, I just want to pile on here. The big change is that binary compatibility is no longer as important as it once was. So that's the bane of innovation is, a proprietary instruction set, that the binary is overwhelmingly important. So in the PC era, the x86 was overwhelmingly important. I'd say in the Android system, in the Apple system, the binary compatibility is very important, but everything else it's not. The edge, people control the software stack. In the cloud, they control the software stack. Verticals control the software stack. So it used to be, proprietary instruction sets and binary compatibility, and everybody else is irrelevant. That's not what the future looks like.
Okay. Krista?
Yeah, I think, speaking of Apple, they just made a big ISA transition. They're probably the companies be most effective at transitioning ISAs. And with the right technology, it shouldn't be a barrier to moving. I think you do have these older software stacks that were built before, this technology was well understood. But yeah, I think translation is a thing. I think one thing I'll have mentioned already in the keynote is that part of growing up in RISC-V is realizing at the beginning we're trying to do a good solution for all these problems. But now we're trying to avoid making it difficult to transition is another goal. Like, we shouldn't be, just for minor technical details, pick a different solution if the standard wouldn't work. We already had that philosophy partly while we're developing RISC-V. We had to port software ourselves in a small group. So we didn't want to make decisions that made it hard to do that. But I think going forward, that's a big demand I see from the community is make it easy to transition to RISC-V. And so don't do things that make it hard to make that transition, even if they seem really exciting and technically exciting. If they are going to make it very difficult transition, maybe we need to think a bit harder about that choice.
Okay. We've got very little time left, and I'm going to ask each of you about now, just to close off, what's the most favorite or fun thing you've seen, which is also a good sort of commercially viable product based on the RISC-V? Maybe start with Dave.
Sorry, I don't keep up with products. I would say the thing I'm most excited about is the security investigation. I want to see what the answer is.
Okay. Who's going to go next in the last few seconds?
Sure, I'll jump in and say that the diversity of the ecosystem is the thing that I find the most exciting. Okay. I think the subsetability of the instruction set, the customizability, the applicability to different domains, I think all these things are the real strength of RISC-V.
Krista, with the last word.
Well, you asked for a fun product. So as a kid growing up in England, I used to watch Doctor Who. So I'm going to brief product plug for the sci-fi Doctor Who themed inventor board. So this is a very fun thing. Buy your kid one of these, get them into RISC-V straight away. But this is a fun thing. It's like a mass market product for kids, education, teach kids how to program. in RISC-V.
On that note, I would like to thank you all very much for a very interesting, fun panel. And thank you all for watching.